Can you hear me in the back? Yeah, that's okay. Okay, welcome to the first lecture on Introduction to Model Checking. My name is Joost Pieter Katoen. I'm a professor here in Aachen since about 2004. And in my group, what we try to do is we try to find bugs. Bugs in hardware, but in particular in software. And as we all know, software becomes more and more important in our daily lives. And sometimes bugs are not catastrophic. I mean, it's a bit annoying maybe if your laptop is not working completely correctly. But if you have a piece of software controlling a nuclear power plant, then it's crucial that this software works correctly. Yeah. Now, there are different techniques to prove rigorously that software has no mistakes. And one of the favorite techniques that we work on, and also one of the, I would say, one of the most popular techniques nowadays is called model checking. And what I'm going to do today is I will give you a bit of motivation background and also explain you a bit about the course organization. Before I start, what you see is that actually the lectures will be recorded. I think there are recordings, but already for quite some years ago, 2011 or so. That means that actually, thanks to the Video AG of the Fachschaft, they will make those videos available. Okay, so I would start with some examples, and one example is a bit old, but it's still illustrating the effects of what bugs in software can cause. So here on the left you see a radiation machine in a hospital, and in particular for cancer patients. So the cancer patient comes to this hospital. They would like to diagnose where is basically the cancer, but also would like to give a therapy. And the therapy then tries to basically, based on the location of the tumor, tries to do radiation treatment. And actually, this was already, as I mentioned, in the 80s. And at least 6 cases of overdoses were reported. And not just a bit of overdoses, no, an overdoses of about 100 times, let's say, the intensity which was supposed to be. And unfortunately, 3 people died because of this. So this is actually a very serious, issue. And the source, after investigating carefully the whole system, the hardware, the software, the radiation machine, it turned out to be the case that there was a design error in the control software, and a bug which is known to be as a race condition. And intuitively speaking, this is something like you have a multi-threaded system, and one task, let's call it A, is waiting for B, but B, vice versa, is in a similar state and waits for A. Then they call this a race condition, and then you can imagine that this can have some consequences. At that time, the software was written in some kind of assembly language, especially for performance reasons. Nowadays, of course, we use most of the time, not always other languages. Another example a bit later was the AT&T telephone network in the US. It was a big problem in New York. It was a 9-hour outage of large parts of the telephone networks. And remember, at those days, we did not have mobile phones, right? So the telephone network was the basic means of communication. This had a severe cost. At those days, $100 million US, but that's already 30 years ago. I mean, now this is, of course, quite a bit more. And actually, it turned out that there was a software in a piece of C code, and there was a wrong interpretation of the break statement in a loop. Yeah, what exactly does the break statement do? And apparently, this led to a bug. The example that most people use if they talk about software mistakes, then it's the Ariane 5 crash in 1996. This was a European Ariane 5 missile, European, which means it's supported by the European Space Agency. And this was launched, I think, in French Guiana in South America. And it crashed after, well, pretty short. I mean, within 1 or 2 minutes after it was launched, it crashed. So here you see the launching, and if you look carefully here, you see that it's basically here it crashes. Yeah. Cost more than $500 million US. What was the bug? The bug was a software flaw. In the control software, what was the idea? They took basically, it was a legacy problem. So they took the software of the Ariane 4. That worked okay. They built on top of this a couple of new features for the Ariane 5. But in the meanwhile, what they forgot was a kind of data conversion that actually converted a 64-bit floating point to a 16-bit signed integer. So you lose some information, and this losing information was essential because it was about the angle of this missile. And if the angle is not correct, there is a kind of auto-correction taking place in the missile, which basically then is a kind of self-explosion. Okay, so you make a measurement. These measurements say, well, we're not on the right trajectory. Boom, it is safe to just explode. Good, this was safe. This was actually written in the programming language Ada. Good. There was some software handler, so there was some exception handling, but the engineers found it to be more efficient to switch off, to disable this exception handling mechanism. So there were basically two causes, right? This conversion plus that the exception handling was not switched on. Good. Just for your information, the French Space Agency at the moment is investing a lot of money in the new Ariane 6. And maybe it's good to know that, to understand that the space agencies are very conservative. So you buy at the MediaMarkt in Aachen a laptop with at least a double core or a quad core, right? I mean, this is nowadays standard. And Ariane 6, they're going to use for the first time in a missile a dual core machine. And not because they would like to accelerate things, no, only because the fact that if one core fails, you still have one core left. I mean, just to illustrate, this is the way that this industry looks. And why do they do this? Because they want to have more than 100% guarantees that things work correctly. And the way they do this now is that, I mean, those engineers know exactly how to program these things, so they are very conservative. Yeah? They used, it's not surprising that indeed this bug was there. I mean, they use for computer scientists, pretty old-fashioned microcontrollers, old-fashioned programming languages, and old-fashioned techniques to check the correctness of software. It's changing a bit, but I think there's much more work to be done. This is a hardware bug of the Pentium floating point division unit. What turned out to be the case, some people that were actually doing floating point division operations, this all worked fine until at some point people were really looking into big experiments, and the accuracy of the results turned out to be very important. And it turned out that 1 in 9 billion floating point operations divides and produces inaccurate results. So it took a very long time before this bug was found, actually. And once it was found, Intel had to basically call back all those microprocessors and had to replace them. So this was an enormous thing. So this was about, well, this is an estimate, but about $500 million and an enormous image loss. It's not only the economic loss, but it's in particular also the image loss of such a company, which is then very severe. Good. What was the source? The source was, the realization of this floating point division, which was not doing exactly what it was supposed to do. I have some later examples examples where model checking has been used to improve those kind of situations. But I think those examples already show you that that software correctness is simply important. Yeah? People don't realize that if you buy a washing machine nowadays, 1 megabyte of software is not an exception. Yeah? So most of the bugs in a washing machine nowadays are actually bugs in software. Yeah? I like to illustrate this statement by Henk Barendrecht. Henk Barendrecht is a Dutch professor from the University of Nijmegen. For those people that are interested in functional programming, the underlying theory of functional programming is lambda calculus. And he wrote the main book on lambda calculus. And he gave a talk at the 50-year celebration of the Center of Mathematics and Computer Science in Amsterdam. And he put it, I think, very good to the point by saying it's fair to state that in this digital era, correct systems for information processing are more valuable than gold. Yeah, so stressing the point that it's simply important to make sure that systems are bug-free. Good. So what we see is a rapidly increasing integration of information and communication technology in different applications. I mean, embedded systems, I already mentioned the washing machine. You can also think about robots, robots assembling your new car, for instance. Communication protocols, the way that communication takes place. So my colleague Klaus Wehrle here in the department develops protocols, communication protocols, and actually he also has projects to prove, to check that those protocol implementations are correct, that they are doing what they are supposed to do. Because according to him, the main problem is that different computers, different engines don't communicate correctly with each other if you don't make sure that the software running on those things is adhering to a certain standard, a standard that describes the communication protocol. So also there you see that correctness plays an important role. And then there is transportation systems. Don't mention the autonomous cars, self-driving cars. It's clear that the software needs to be correct, right? Nowadays, they use machine learning techniques to, you have sensors on those cars. Those sensors, they detect certain objects. And now you have to check whether those objects are human beings. Are they moving? Are they obstacles which stand at a certain position and are basically fixed there? Are they static? And based on that information, the software controlling the car makes certain decisions. Yeah? Now, how do you guarantee that this works correctly? Yeah, and this is a big issue at the moment, and therefore people are looking into verification techniques more and more. So it's fair to say that reliability increasingly depends on software, and we have also already seen that defects can be fatal and extremely costly. Safety critical systems are, of course, I mean, autonomous cars, nuclear power plants, these kind of things are, of course, safety critical. But also think about small products which are distributed among masses. And so there are projects subject to mass production. One of the first examples we worked on was a communication protocol between a control unit, so an infrared control unit, with a television set. Okay, now you might say, okay, if it doesn't work, I just simply push the button twice, right? If it then works, it's still okay. So those bugs are, of course, not very costly. They're a bit annoying, perhaps. Nonetheless, by means of model checking, we found some bugs there, and that was for the Dutch company Philips. And they actually, at those days, it was not easy to really do the software patches like you do now. Where basically you have to download every day now a new update of your whatever kind of software, because a bug has been found and a patch has been made. But there they really had to basically call back those infrared remote control units, and they are very cheap on their own. Yeah, but if you have sold 1 million of them, then of course this becomes an issue. So what is system verification? So here is a folklore definition. So what you would like to do is you check whether a system fulfills the requirements that have been identified. So typically, if you look at engineers write requirements. These are typically thick documents where the requirements are written down in some natural language. Yeah? Don't mention logics there, they're just natural language. And then based on these requirement documents, typically documents of 100 pages or more, they start building the system. Yeah? And then in the end, you have built your system and you would like to check whether the system works correctly. And that means, does it meet the requirements we started from? Yeah. Good. So verification is, check that we're building the thing right. That means basically that we are doing the right thing. And sometimes people call validation that check whether we are building the right thing, which is sometimes a bit different. So what kind of technique are people using in industry? If you look at software, then the typical step that people do is by peer reviewing. So you have a team of developers, they develop the software. You like to check whether this software is running correctly. What are the people doing? You give this software, after doing some static analysis and some standard stuff, you give it to another team, those people that were not involved in developing the software. And then basically they do a manual code inspection. Yeah. Manual. And they find already about between 31 and 93% of the defects with a median of about 60%. These data actually come from the studies of actually German software companies a couple of years ago. But of course there are subtle errors. I call them corner cases. And those corner cases are hard to catch. Maybe if you have a very experienced programmer, they will find these kind of bugs. But typically you don't find them. And we're talking about defects in algorithms, but in particular also defects in concurrency when you have multi-threading. And I have one example later on. Another technique that people use a lot is testing. So what is testing? You take your implementation, your piece of code. You would like to check, does it work as it is supposed to be working? What do? You just issue a couple of tests. Yeah. And then you try to see whether the output conforms to the requirement. Okay, but of course, in order to do this exhaustively, you need many and many tests. In particular, it could be the case that you need infinitely many tests. So people take some arbitrary set, do some selection, and based on that, they decide whether the software is okay or not. So this is a dynamic technique. You really run the software. That's the difference with the peer reviewing. But of course, you are limited to the test cases you are considering. So if you look at the software project cost, about 30 to 50% is devoted to testing, and more time and effort is spent actually on checking whether you are doing the right thing rather than on constructing. And this trend is something that you might question. And what's a defect density? This is a number of Microsoft, and I get back to Microsoft a bit later. At those days, and this was I think Windows 95, Microsoft said, well, the software is okay if we have about one defect on every 1,000 code lines. And 1,000 code lines, I mean the code lines without documentation, so without the comments and so on, so the real code lines. Yeah? But I get back to this later about Windows. Okay. So here is a picture, and this is not really a linear scale, but it's only you have different phases. So it's not indicating that every phase takes equally long. So you typically have some analysis of the problem, then you do some requirement specification, then you do conceptual design of your system, then you start real programming, then you maybe do some unit testing, so you test the individual parts of the system or the individual parts of your program. Then maybe you do the testing of the entire system, where the units need to cooperate, and then maybe the system is in operation. Yeah? So as I said, don't take the length of every phase as equally long. I just want to illustrate that you have those different phases. And this is the time, right? Good. And now there are two y-axes. Here on the left, it tells you what is the percentage of errors. Okay? So what you see is that according to this curve, and this is based on empirical studies, most of the errors are introduced in the conceptual design and during the programming. But here you see that the number of errors is actually going down. Yeah, good. Then the green curve tells you when the errors are being detected. So initially, of course, bugs will be detected. Here, bugs are detected, but most bugs are detected, well, some of them during unit testing, but most of them if you test the entire system, which is not so surprising, perhaps. And then the red curve is now we have to look at this y-axis. This is the cost of correction one single error in the unit is $1,000. Yeah, so if you find an error here, it's relatively cheap, right, close to zero, to repair the error. If, however, the error occurs here, then you're already in the phase of system testing, then it is more, it's more involved to basically fix the error, and therefore it's more costly. And of course, if the system is already in operation, so you have launched the product on the market, then it's even more costly, as you can imagine. Yeah? And then the estimates here were about $12,500 US, which to my opinion is still a kind of underestimation. But so the slogan here is, and that's also the top of my slide, bug hunting, the sooner the better. What you would like to do preferably is to basically to close the gap between, put it bluntly, the blue curve and the green curve. Try to bring them closer together so that you are earlier in your design, you're able to find the bugs. So what I'm going to say here is that not model checking is the silver bullet. It's not the solution to all problems. But here you typically have already some models, and maybe it's good already to check properties on models. Later you have code. It's also good to check properties on code. Yeah? And then maybe you then do an installation on hardware, and maybe then it's good to do testing. Yeah? So I'm not saying one is much better than the other one. I think you need definitely all of them. But techniques like model checking help a lot to bring these things together. Okay, so I'm working in the field of formal methods. I call them always, they're applied mathematics. So in this course, what we're going to do, we're going to talk about graphs, we're going to talk about automata, we're going to talk about logics, because that's what's underneath. Yeah? So it's for modeling and analysis ICT systems, information and communication technology systems. Some people believe that formal methods offer a large potential to indeed do this early integration. Remember the two curves? You would like to do verification and modeling as soon as possible in the design process. You would like to get a verification techniques which provides you with a higher coverage. You would like to find more bugs than just doing by testing or by doing peer reviewing. And in the end, you also would like to reduce the verification time. Remember, 30 to 50% in a software development process is devoted to testing or to code inspection or to static analysis. The use of formal methods nowadays is also in standards highly recommended. So you have a standardization body. So this is the Federal Avionics Authority. So this is a standardization body that is about airplanes in the US. And they have different criticality levels of software. And for the two highest levels of software criticality, they recommend to use formal methods like model checking. NASA actually also uses formal methods and actually advocates the uses of formal methods in safety critical software. And there is a standard for self-autonomous cars. So there is a standard called ISO, which stands for the International Standardization Organization. And then there is a number 26262. If you Google this, you get tons of hits. There's a new standard, and actually the car manufacturers have to adhere to this standard, I think, by the end of this year. And this means that car manufacturers, and of course everybody knows the importance of car manufacturing in Germany, are seriously now looking at these standards. And in this standard, they have different levels of integrity. They call this ASIL levels. I think you have something like ASIL A to D. And the highest level, D, that means that your system is only allowed to have about, I think, I do this at the top of my head, 10 to the power minus 9 errors, right, during the runtime. So very low. And the standard is advocating to use formal verification like model checking. So there is more interest actually also by the German car manufacturers to look at model checking. Good. So there are different techniques to do formal verification, and I just want to basically illustrate the difference between them very globally. So there are what they call deductive methods. One of the deductive methods that you're probably familiar with is you take a program you like to prove that this program is correct. Now, in the lectures on programming, you have learned that you can then, and to my opinion you should, define a precondition and a postcondition. And what's the hard part to reason about programs? The hard part is to reason about loops. Yeah, you would like to capture the behavior of a loop, and what do you need for doing this? A loop invariant. Now, in general, it's undecidable to find a loop invariant. That's why the problem of program verification is in general computationally intractable. But you can, of course, try to support this. And for instance, one of the ways to do that is that you basically use fear improvers or proof assistants to assist you as a user to prove, for instance, small lemmas already about your program. You basically have a guess, well, the property should be that, well, x is always at least y. Let's try to prove this. And then the fear improver can assist you whether this is the case or not. And this is definitely applicable. One of the drawbacks of deductive methods is that there is a high, I would say, interaction with the human. So these techniques, and I think I have a slide on this, have been developed. Actually, the first paper was by Turing, end of the 40s, and then later in the 60s, people have developed these deductive methods. And then early 80s, two pairs of people, I come to them in a minute, have developed the technique of model checking. And there the idea is not basically to look at the syntax of your program. That's what you do if you write pre-post conditions and loop invariants. You don't run the program, you don't build an automaton of the program, you just look at the code, right? That's all. In model checking they thought, well, why don't we make a model? Yeah, and why are we not going to analyze this model and systematically do this by means of algorithms? This is maybe, of course, not complete, right? There are cases that we cannot cover, but I hope we can find many bugs. So we systematically check a certain property P, and you do this, for instance, in all states of the model, and think about an automaton kind of model. Yeah. And there are several tools that actually do this, and this is, of course, applicable if you can find a finite model of your system. Yeah. During this lecture, we'll also learn that for some infinite state models, you can still do things. And then there is another technique which is called model-based simulation or testing, and that's what I already mentioned. This is this test by exploring possible behaviors. Why do I mention this as formal verification? This is a sentence which is slipped off here below. If you have a formal model of your system, you can use this formal model to do automated test generation. So it's not the case that an engineer on Sunday says, okay, let's test this. No, you use the formal model, basically the requirements, to steer the test generation process. Good. Milestones in formal verification. The first paper that mentioned the need for mathematical program correctness was by Turing. At those days, programs were data flow diagrams, so no textual format, just a visual format. And he literally gives a proof why this data flow program is correct in the sense that it adheres to the specification. In the 60s, there were several people. Floyd was one of them, but I only mention Hoare here. There the idea was to do syntax-based techniques. So you take a program code, and what you try to do, you annotate the program with postconditions, preconditions, loop invariants, and based on that you prove that the system, for every state satisfying the precondition, the program terminates and it establishes the postcondition. And what you do there is you use mathematical logic to predicate logic, so typically first order logic, to reason about these kind of things. So that core questions was, given a certain input, does the program generate the correct output, or are for all possible inputs generating the correct output? And I mentioned they have proof rules, and I have some of them on the next slide. And the strength of this technique is that it is compositional. What does that mean? Now, if I have a program consisting of several parts, so suppose very schematically I have a program P, followed by a program Q, followed by, I don't know, while x larger than 0 R. Then what this technique can do is it basically can make a statement about P. So you first try to formally verify P, then you formally verify Q, and then you formally verify this part. and then you can combine the results. So the strength of this technique is that you can look at the components of the program in isolation, analyze them in isolation, and then combine the results to get a result about the entire program. Good. This was for sequential programs. And then actually Amir Pnueli from Israel, he developed a syntax-based technique, so he tried to extend this for concurrent programs. So he was saying, no, we don't have a sequential program, but maybe we have this program as a thread, and this thread runs in parallel to some other program that does, I don't know what, Q followed by T. Yeah? And his philosophy was similar. Can we now analyze this part in isolation of this part as far as possible, and then try to combine the results? And he was the father of introducing actually temporal logics, and temporal logics are the logic that we are going to use in this lecture as well. So here it was predicate logic. It was enough to make statements about the pre-condition, the start of the program, the post-condition, the end of the program. Pnueli developed a technique where he was mentioning and he was stressing the fact that it's also important to make statements about what happens during the program. And for that, he actually used temporal logic. He is not a developer of temporal logics. Temporal logics have already been developed, for instance, in philosophy in the 50s, but he was one of the first to introduce it into computer science. Famous paper in 1977, Fox. Okay. So basically, Pnueli generalized what Hoare was doing, but then for concurrent programs. And then people found out that maybe what we would like to do is to do an automated verification, because these two techniques you have to find invariants, you have to find those properties yourself, maybe with the assistance of a theorem prover, but it's hard. Maybe we can do a little bit more modest, try to restrict ourselves to finite instances. So we're not going to solve the entire problem, of course not, because that's undecidable, but try to restrict ourselves to finite instances. Typically hardware has finitely many states, so the first actually popular application was hardware verification, not software verification. And there the idea was, rather than using proof rules, we're going to use models of the system. And then the question is, does a model of, for instance, a concurrent program satisfy a certain property? And these properties are typically specified in logic, and people are using different variations of temporal logics. So here are some slides of, here's one example of the rules this is the Hoare approach. So this is the approach here, the syntax-based technique for sequential programs, later extended by Pnueli. And what you see here is that, for instance, what can you say about an assignment? So the way to read this is that if the top is true, you can conclude what is written down below the line. If there is nothing, it simply means true. So the premise here is true. And the proof rule says, suppose that I look at an assignment that I basically assign to x the expression e. Now, if my post condition is a formula a, then what is the precondition? This is a where you basically have replaced x by e. Yeah, so the way is that you reason backwards. That's maybe a bit counterintuitive for you, but you start with the post condition and you are going to argue if this holds, what is then the precondition. Here is something for a loop. Suppose that the loop body is p, and suppose we know that if I stands for an invariant and Boolean condition b holds, when p starts, p will terminate and will establish the post condition, the invariant will still hold. What can you then say about the loop while b do p? Then you can say the following. If the while loop starts in a state satisfying the invariant, then on termination the invariant will still hold, and because the loop has terminated, also the negation of the guard has to hold. Yeah? Good. The same you see here, something about sequential composition. If I want to prove that P followed by Q establishes C when it starts in the state A, one way to prove this is by means of the following rule. You take the two components, remember compositionality. I would like to prove something about P, I would like to prove something about Q, and then combine. That's what this rule illustrates. So I try to prove this for P. I try to prove this for Q. And what's essential is that this post condition is equal to this precondition. And of course, you can also do, you have logical rules that say, for instance, if I know that P starting in a state satisfying A prime will terminate and then establishes B prime, and suppose I can prove that A implies A prime, then I can replace this A prime by A. Yeah, because I know if for every state that A prime it starts with, it will establish B prime, then of course if A implies A prime, then also for every state where it starts in A, B will establish in the end, well, B prime, but if B prime implies B, I can also put B there. Yeah? So here you see that you do not always have to have exactly B, but this rule allows you to actually do also implications. Good. I don't want to go in depth in this, but this is only to illustrate these techniques, and these were the techniques before model checking started. And don't get me wrong, these techniques do still exist. They have their existence in their own right, absolutely. I only want to schedule here or tell you what have been the developments of formal verification over the years. By the way, all these people, apart from Turing himself, Hoare, Pnueli, the people that developed model checking, they all received the Turing Award. Okay, so here is an overview of what model checking does. And this is also giving you some indication what we are going to do in this lecture series. So the idea is that you start with requirements. You have to formalize them. Why do you have to formalize them? Because I would like to know exactly the property that we need to check. It cannot be some kind of vague statement. It needs to be a precise, unambiguous formulation where we start from. This is the phase that we are not going to take in this lecture series. We will start from a property specification, and this will be done in terms of logics. I only want to stress that this part in practice turns out to be very hard. So we recently, last year, did 2 case studies for Ford, the car manufacturer, and we looked at software of about 5,000 to 10,000 lines of code. And the question by Ford was, can you do formal verification of our thing? Okay, we said, okay, give us the requirements. So they gave us a FIC document. 40% of all the things we found were bugs, inconsistencies, unclarities in the requirements. Yeah? So because we had to do this, and of course certain requirements were incomplete. Then the engineers said, but this is common knowledge. Yeah, common knowledge maybe by the engineers, but not if you want to do formal verification, right? So what I'm saying is that this is a phase that we are not going to confront with in this lecture, but it's not something that you should neglect. Then the system is modeled by some system model, typically a kind of transition system. And then both the property specification and the model are given to a model checker. And now typically there are 3 possible outcomes. So here are many algorithms. And in this lecture we are going to focus basically on what is in this yellow box. There are possible outcomes: satisfied. Satisfied means this model satisfies this property. Yeah. If you do this wrong, rubbish in, rubbish out. Yeah. If the model is not the model you want to check, no guarantees about the results of the model checking. Yeah. So the assumption is always the model is an adequate representation of the system, the property is an adequate representation of the requirement, and then you can do model checking. So this means the model satisfies the property. It does not mean the system satisfies the property. It could be the case that the property is violated. And then the strength of model checking is that model checking will also give you a counterexample. So it will give you diagnostic information why the model is violating the property. And this is very helpful. And this is why some people actually claim that model checking is most useful as a kind of a clever debugging technique. Yeah, because if you find a bug, you get some information and maybe you can fix at least what you're doing. So typically you get a counterexample, you can simulate the counterexample, hopefully get some information about where is the bug, and then this is helpful maybe to fix what you're supposed to do. Sometimes this means that you have to fix the model. Sometimes it turns out that you're not checking the property you want to check, so maybe you made a mistake here and you have to go back. And sometimes you found a real mistake. That's also possible. And then there is a third possible outcome. This has its insufficient memory. This simply means a segmentation fault core dumped. This simply means that your model is too big to be handled. So one of the main issues in model checking is try to treat the largest models possible. And models are millions of states, billions of states, trillions of states. Okay? So there actually clever techniques are needed to reduce these kind of outcomes. Okay, I just want to show you the influence of model checking by a couple of results. And I mention here a couple of awards. And one of the awards is the Paris Kanellakis Theory and Practice Award. Paris Kanellakis was a famous Greek researcher in algorithmics. Unfortunately, he died in an airplane crash. But after that, there were initiated this Paris Kanellakis and Theory apart. And these four people, Randy Bryant, Ed Clark, Alan Emerson, and Ken McMillan, they received this prize. And I took this text for the invention of a model checking technique which is called symbolic. And this is a technique that actually is used heavily to try to combat this state space explosion problem. So to deal with enormous large state spaces. Still finite, but enormous large. So what they do is, symbolic model checking, a method of formally checking system designs, which is widely used in the computer hardware industry. This is 1998, right? So 2 years ago. Hardware industry. Yeah. And starts to show significant promise also in software verification. So I will tell you that later. Nowadays, in software verification, I have some examples. People are using more and more model checking. Some other winners of the same prize to give you some indication about the importance of this prize. Paige Tarjan. Paige Tarjan developed things like balanced trees, plate trees, all kind of data structures that you can use to do efficient operations. Depth first search, one of the key algorithms for graphs, is developed by Robert Tarjan. Yeah. Minimization algorithms for automata, which is a standard kind of technique. They developed a very efficient algorithm to do this, which is logarithmically in the number of states. Paige Tarjan, partition refinement algorithm. Rivest, RSA cryptography. Rivest, the R is from Rivest. Yeah? So this is some indication about this prize. Another one is the Gödel Prize. Gödel Prize is an important prize in mathematics. This has been awarded in 2000 to Moshe Vardi and Pierre Walper. Moshe Vardi is someone from Israel. He's currently in the US. He's a famous guy in theory, logics, automata, games, AI, knowledge logics, and so forth. Pierre Walper is actually in Liège, around the corner here. He's currently the dean of the engineering department there. And they got this prize for work on model checking with finite automata. So they were the first to use old-fashioned finite state automata to do model checking. And that's the theory we're also going to see in this lecture. Some other winners. This is hard to pronounce. He proved that something about deterministic pushdown automaton versus non-deterministic pushdown automata. Agrawal et al. Are those famous people from India that showed that if you would like to check whether a number is prime, you can do this in polynomial time. And Shor did something in quantum computing. He showed that certain algorithms can be much, much faster if you have quantum computing. What I like personally a lot is not just theory, but also to bring this theory into practice. And there is the ACM System Software Award, an annual award awarded by the largest society in computer science, ACM. They award this prize to the things you are aware of. The developers of tech, the developers of PostScript, the developers of Unix, TCP/IP, Java, Smalltalk. Maybe you don't know what is Smalltalk. Smalltalk is an object-oriented language that was the predecessor of C++ and so forth. They all got this award. Holtzman, he is the person that actually built the first model checker. I'm not sure whether this is completely true. The first large model checker, let's put it that way. That's called Spin. You can download it. If you want to play with model checking, I strongly advise you to download this tool. There's also a book called the Spin Model Checker that gives the details. And Spin is a popular open source software tool used by thousands of people worldwide that is used for the formal verification of distributed software systems. Good, and the last thing, but I already mentioned, was the Turing Awards. Clark, Emerson, and Sifakis, and this is a bit of a story. So in 1981, there were two papers. One paper written by Clark, and at those days his PhD student, Alan Emerson. And there was another paper written by two French people, Joseph Sifakis, Grenoble, and his student, Quelle. Quelle, very soon after his PhD, quit science. Maybe that's the reason why he's not mentioned here. But those three people got the Turing Award actually in 2007. And for their role in developing model checking into a highly effective verification technique widely adopted now in hardware and software. So you see the change from 1998, hardware, 10 years later also software. Other winners of the Turing Award, I guess you know them all. Edsger Dijkstra, Stephen Cook, Tony Hoare, Robin Scott, non-deterministic automata, etc. Okay. So what is model checking in a nutshell? Model checking is an automated technique, so we will talk a lot about algorithms that takes as input a finite state model, a formal property, typically written down in terms of a temporal logic, in a logical formula, and what it does, it systematically checks whether the property holds for that model or for a given state. For instance, the state in which the system will start. That's the typical kind of thing. What are models? This is a model of a mutual exclusion algorithm. There are two threads. This is an algorithm that we're going to describe later in detail. It's called Peterson's bakery algorithm. What is a bakery algorithm? You go to, on Saturday morning, you go to a bakery shop. Everybody wants to get fresh bread on Saturday, right? So there's a long queue. So what do you have to do? You have to get your ticket. There's those numbers on the screen that tells you when it's your turn. So you come in, you pick a new ticket. Yeah? And if it's your ticket is shown on the display, you get your turn. So this is the core actually of this Peterson's algorithm. And what is this? This is for two threads, but it also generalizes to many more threads. And this is a transition system, so an automaton, where you keep track of the states of every thread. So the subscript 1 tells you something about thread number 1, subscript 2 tells you something about thread number 2, and apparently thread number 1 has a variable called x1, thread number 2 has a variable x2. These are the ticket numbers. We start with 0, and then you see those ticket numbers increase, 0, 2, 0, 3, etc. This is actually a model which is infinite. So this is an automaton or a transition system, as we're going to call it, which is infinite, countably infinite many states. And this is an example of a model. Okay. What are we going to learn? So we're going to learn in this lecture series that these models are called transition systems. What are transition systems in a nutshell? And we get to the formal definitions, of course, in the next lecture. We have states. States are labeled with some basic propositions, properties. Maybe in this state, we would like to say that x1 is at least 0 or x2 is less than 10. These are kind of elementary basic properties. So these are logical statements about the state of your program, the state of your hardware, the state of your traffic light, the state of your car, etc. You have transitions between states that tells you how the system evolves by, for instance, in terms of a program executing a statement, and you go to the next state. And these transitions actually are labeled. And why is this? Because I would like to build those automata, those systems like this, not as this big spaghetti structure, but I hope to be able to start with the model for thread number 1, the model for thread number 2. Hopefully they are concise and comprehensible. And then I would like to have means to combine these models into one model, which looks like this. Yeah? So compositionality, but not in this sense, but in the sense of combining models. And that's what we're going to do by means of labeling those transitions with actions. So it's not an automaton that you feed with a word, and based on the next symbol, the automaton makes a decision. Here the symbols will be used to combine things. Okay, what we are going to see, and we're going to start with this next week. I'm going to show you that transition systems are the model that is key to model all kind of different things. So if you like computer programs, we're going to see that actually a computer program can be represented by a transition system. So we're going to see how you can map from code to a transition system. Then we're going to show that multi-threading. So you have now parallelism. Also this can be modeled by means of transition systems. Even if those threads are communicating, which means either they have a shared variable or they have some communication means like a channel, and one thread can send a message to another thread. This can all be represented by transition systems. I'm going to show you that you can model hardware circuits as transition systems. So actually what this means, we're going to focus from there on model checking transition systems. So the models that we're going to use are transition systems. And the first thing I'm going to show is that many things, not all, but many things are transition systems. If you like Petri-nets, Petri-nets are transition systems, etc. So these are models. What are properties? Now, let's first look at some example properties. You would like to check whether the system can at some point reach a deadlock situation, a situation where no progress can be made. Yeah, this is typically bad. Typically. Yeah, termination of a program is also a state where you do not make any further progress. That's typically good, not bad. Can two processes, so think about something that you have a system that is sharing a resource, and you would like to have that only one process at a time can use this shared resource, things like mutual exclusion. You would like to check, can two processes ever be simultaneously in a critical section? That's a situation you typically like to avoid. So this is a property that you like to express. Yeah, so actually we're going to use quite a couple of mutual exclusion algorithms and different kind of properties to show how this works. If the program has terminated, does the program provide the correct output? That means is the output corresponding to the post condition? And what we're going to do in this lecture, we're going to use logics. Yeah. So we're going to use propositional logic and or negation, etc., standard stuff. And we're going to equip this with some modal operators. Things like always, it's always true that a certain property holds, or this thing is called eventually, which means eventually you reach a state that satisfies the property in quotes eventually. The main paradigm shift with the lecture you are aware of in automata theory is actually now we go from finite words, finite state automata, to infinite words. So actually we're going to interpret these kind of formulas not on finite sequences but on infinite sequences. No? That's one paradigm. They call this the linear paradigm. You have linear temporal logics that are interpreted over linear structures, and our linear structures will be infinite sequences of states. There is also the possibility to interpret logics over infinite trees. And then we call these logics branching logics. And what we're going to do, we're also going to see some logics that actually are interpreted over infinite trees. Good. I have one example. It's a piece of code from the NASA's Deep Space One spacecraft, abstracted a lot. And people have used, in particular, Holtzman and his team, the guy that developed SPIN. By the way, he's the head of the group in the Jet Propulsion Laboratory in Pasadena, which is part of NASA. So he's now applying this kind of stuff to NASA, and actually at those days he was already doing this. This is a picture of the NASA Deep Space One spacecraft, and he has applied model checking to several modules of this spacecraft. So one example I'd like to give you is this program fragment. We have 3 threads and one shared variable. The shared variable is called x here. And the property we're interested in is x always between and including 0 and 200. So in terms of a logical formula, we're later going to see, we're going to express this as box 0 at most x at most 200. That's the property. And what's the system? The system is a 3-threaded system. We have a thread inc. It says it's an infinite loop. If x is strictly less than 200, increment x by 1. The second thread is similar but decrements x. So it says, okay, I have an infinite loop. If x is larger than 0, then decrement x by 1. And here you have a process reset. It says if x is 200, then we start in 0 again. Okay? My question to you is the property, is x always between 0 and 200 true?
If x is 200, then decrease was...
X is 200, yes?
Yeah, and then the second process was implemented.
The second process tests whether x is larger than 0?
Yeah.
Yeah?
To the critical section, but then the last thread was executed.
This one executes first, x becomes 0,
Yeah, and then the x...
and then x goes down. So x becomes minus 1.
Yeah.
Yeah? Agree? Yeah? Now you can also model check this. So this is the code that you can put into the spin model checker. The input language is called Promula. I only use a fragment of it, and that's my quote of the fragment. It's the nano fragment of Promula. So here you see initially we have a global variable, it's x set to 0. We have 3 threads, inc, dec, and reset. And we have the main module. The main module says, okay, you run inc, you run dec, and you run reset. And I do this atomically, which means I don't want to have any difference between first starting inc, then first starting dec. I would like to start them at the same time, basically. So this could make already one step, and that could make one step. I first would like that those threads are doing a step if only they have started all together. That's why I use this atomic statement. Good. The rest of the code is literally a one-to-one correspondence to what we have seen before. Do stands for while. So do odd is a loop. If the guard is true, then if x is strictly less than 200, increment x by 1. This is the decrement thing. It says, okay, infinite loop. If x is larger than 0, decrement x by 1. And you have the reset that says, okay, infinite loop. If x equals 200, then set x to 0. So the syntax here is that one equal sign means assignment. I hate this. I mean, assignment is not the same as equality, right? It's the two different things, to my opinion. But okay, let's keep that. And then you have to make another syntax for equality, and then you get double this symbol. Yeah. Okay, you run this in your model checker. Yeah. How do you check this? First, I have to express this property. Now, I did not introduce you temporal logics yet. So what we are going to do is the following. We're doing a small trick, and this trick is the following. We're going to take inc, then we had basically parallel, I write it down here symbolically, dec, and we had this reset process. And I take this whole system, and I'm going to put in parallel what I call a monitor. So this is a kind of a process that has no side effects, but it's going basically to check what are the other 3, inc, dec, and reset doing. Yeah, so syntactically, this process is going to check. So the idea is basically that this is a checker of what? Well, that x is this. Yeah? So the way to write this down in syntax here is that, okay, I call this process not monitor but check. And what it does, it asserts. Assert means you're going to check for all possible scenarios that this condition holds. And this is exactly the condition we were interested in, right? That x is between 0 and 200, including the bounds. And now I changed my core. The core is now your inc, dec, reset, and the checker. So basically you start this process. Yeah? So think of this as a kind of a watchdog. It monitors what's going on, and it is going to raise an alarm if something goes wrong. So it's going to raise an alarm if these 3 processes reach a state where x is not satisfying this Boolean expression. So we run, and this is the output. So the spin says error assertion violated. Good. So this means the model that we put into the model checker violates this assertion, which means this monitor has found a state where x is not between these bounds. Good, that's good to know. Now you like to know why. As already was pointed out, this is exactly the scenario that the model checker generates. So here you see it needs a couple of steps to do that. So it needed 600 so many steps to find this scenario. Yeah, but it did this completely automated. Yeah. So the crucial point is the following. You see here that there's exactly the scenario that was sketched in line 609. The token was, so reset, the process reset was scheduled, and it checks that x equals 200, which seems to be true. And you can see that this is true because here you see that x was less than 200, x is incremented by 1, and apparently this was the last increment that made just x equal to 200. Yeah, so equal x here is just 200. Now you reset x to 1, to 0, and then you see that basically decrements checked already before, namely here, decrement checked that here x is larger than 0. This was true. This was true because x is equal to 100. So, but you see the crucial point is that this has been reset to 0 before you decrement, and then x becomes minus 1. So it's exactly the scenario you pointed out. And now Spin also has the possibility to find you the shortest counterexample, maybe a counterexample that does not need to have 600 so many steps, but gives you a shorter thing. So what you see here is that you get diagnostic information why the system does not satisfy the property. And we're going to see what is the machinery underneath to get these kind of counterexamples. Good, how can you fix the error? What is the problem? The problem is you test x, and then somebody else means another thread can come, change x, and then you execute it. You just check the guard, you execute the body. And in order to avoid this, you can fix this by saying, for instance, atomic, which means everything that is in between those two braces means that you do the test and the change of x as one atomic statement. In terms of an automaton, one transition. Okay? So now the scenario that was just sketched before, that this thread checks whether x is larger than 0, then this one checks that x equals 200, sets x to 0, and then this one gets to minus 1, is not possible anymore. Yeah? Good. And now you can model check this, and the model checker says property is satisfied. Okay? Good. Okay. So how do people use model checking? So there are 3 phases. First, you have to model your system. You maybe can do some simulations to check whether the model is really, as a kind of first sanity check, whether the model is really modeling your system. Then you formalize the property to be checked in logics. Now you run the model checker. This is push button. Yeah. I recently was giving a talk about model checking at Bosch R&D, and I told them, yeah, it's push button, but you need to know which button to push. I mean, typically it's not just one button, but you get a whole menu of buttons, and you have to know which button to push. But then the hard part is actually the analysis. If the property is satisfied, okay, fine. You can check the next property, if there is anything left. If the property is violated, yeah, then, okay, this counterexample is useful. So you are going to check this counterexample. Maybe you're going to use simulation to check what is exactly the scenario, or maybe you're going to look exactly at this text. Now, this looks still a bit comprehensible, but remember, there are 600 so many lines before, right? You have to find the right spot. Then you have to maybe refine your model. Maybe your model is not adequate. You found maybe a counterexample, which is a behavior that the real system does not have, but your model has. How can this be? Yeah, maybe you made a mistake in making your model. Maybe the property, maybe your counterexample is giving some scenario that you still like, but maybe you did not check the right property. Could be. Yeah. And maybe you have to check your design. Maybe it's a real bug, and maybe you really have to change your system. Good, so this means that you have to do this, and this is typically done by human beings, right? This is not automated. And then, of course, you can have the message segmentation fault core dumped. Yeah, then you have to try to reduce the model and try again. Good. Model checking is not a solution to everything. It has several advantages, so I listed here some. It's widely applicable, many applications. You can check for what I call partial verification. If two properties are the prime properties, you only check those two, but you don't check the rest. It's potentially push button. It's a rapidly increasing industrial interest. I think the strength is in particular if your property is violated, you get this counterexample. What I like a lot is that, of course, there are many mathematical foundations. It really builds on discrete algorithms and data structures and algorithms. It builds on top of graph theory. It builds on top of automata theory. It builds on top of logics. And those things are coming together. And therefore, I think this is a very nice application of these kind of different fields. And the strength is in particular, it's not biased to the most possible scenarios. It's not biased to those scenarios that maybe you used for testing your design. It's biased to nothing, yeah? Because it checks, basically, it does a systematic check of all possibilities. There are also cons. So mainly it's focused on control intensive, so less about data. This is shifting a bit, but it's basically about, is the control structure of your system correct? I already mentioned rubbish in, rubbish out. Model checking is as good as the model. No guarantee about the completeness of results in the sense that you check now 10 properties. This does not give any guarantee for property number 11, property number 12, etc. It's in general impossible to check generalizations. And what do I mean by this? Suppose that you have a distributed system. Yeah, and suppose you have a system that contains is a ring. Yeah, maybe this ring has 5 processes, and processes can send messages around like this. And maybe if you're lucky, you can model this in spin, and you can do model checking. So what do you do then? You check a property for a system consisting of 5 processes. Maybe you can do it for 6, maybe you can do it for 7. But I'm in general not able to make a conclusion that by induction, it also holds for any arbitrary size. Yeah? So these kind of generalizations are in general, there are exceptions, in general not possible. Nevertheless, model checking is a very effective technique to expose potential design errors. I would like to give you, to my opinion, some striking examples where people have used model checking to find bugs. So the first example is an encryption protocol developed by Needham and Schroeder. I think developed in, what was it, 79, was it 79? Something 79, early 80s. So this is an encryption protocol that has been used in extensively, implemented extensively, and after 17 years, Gavin Lowe, Oxford University, made a model of this protocol, did exhaustive model checking, and found a corner case that was a bug. Okay, now you might say, it has been implemented, it has been running for 12 years, who cares? Well, if you're interested in encryption, you do care. Yeah? Even if you don't have found this bug already by running the system for 12 years. Yeah? Transportation, there is a nice case study, I think it was in Denmark, where they built a train model of so many states. Try to imagine how many this is, right? This is enormous, right? I mentioned already you need to cover many, many states. They did very clever techniques, compositionality, symbolic structures, and so forth, to be able to check properties on a train model of so many states. There are model checkers for not only for models, but nowadays, I already mentioned the shift from hardware to software. Nowadays, actually, there are direct model checkers that actually check C code, Java code, C++ code. And they're used by several companies. Microsoft, I have some slides on this in a minute, Digital, NASA, and I will tell you something about the success in Microsoft about device drivers. So what we did in the last 5 years in my group is we built a model checker for Siemens, German company. They were interested in verifying what they call programmable logic controllers. These are small pieces of programs, typically a few hundred lines of code. They control machines. Yeah? And what we found is we found in 2 examples bugs. And then, okay, the alarm bells were going off. And then they said maybe we have to invest in formal verification. And actually they funded a project with 2 PhD students. One was located and still is located in Aachen. And what we did is we built for Siemens a model checker. The model checker takes as input PLC code and tries to check and find bugs in PLC code. So you see that also in those industrial partners, companies, more and more interest is in verification. I will tell you a bit about this example because I like it. It's a Dutch storm surge barrier in the Nieuwe Waterweg. And there is software in several generations of the space missiles. I already mentioned the Deep Space One, but this is the group of Holtzman, a jet propulsoring laboratory in Pasadena. He is head of the LARS group, and this LARS group does model checking. There's a very nice paper of him, 2014. Maybe you remember this Mars rover. It was something that was supposed to land on Mars, but it crashed. I mean, the landing went wrong. Yeah. So what they did, and there is a nice paper about this that analyzes what went wrong in the software, and they then, unfortunately, a posteriori, checked this by model checking, and indeed were able to replay what went wrong. Yeah. Okay, this is the kind of application areas of Holtzman. So let's look at this storm surge barrier. So let me, as a Dutch guy, try to learn you something about the Netherlands. So if you look at the Netherlands, very schematically, it's something like this, right? Very schematic. Here is Aachen. Yeah, here is Aachen. Yeah, it's almost on the border. Yeah. What is specific about the Netherlands is that a lot of the surface of the Netherlands is below sea level. Now, I don't know exactly how much, but I would guess something like this is below sea level. Yeah? So here we are safe. Yeah? But in 1953 there was a flooding, and this flooding, I think, hundreds of people were killed. And basically because this area, and this is a bit schematic, but here are some islands. It's called Zeeland, a very popular holiday resort for Germans here. And here was actually the flooding, and actually many people were killed. And then the Dutch government decided to build what they call the Delta Works. And the Delta Works are many dams and many, let's say, dikes, etc., to prevent the country from such a flood again. And one of the last building blocks was what they call the storm surge barrier, and that is close to Rotterdam. So here is Rotterdam, one of the largest harbors of the world. And here the ships come in and get into Rotterdam and go back. So what they built as part of this was the Maaslandkering. What is the Maaslandkering? Here I have this is a prototype model. So here is 2 arms, right? Here is 1 arm, and that's 1 arm. If this system is closed as it is depicted here, so think about here is the sea, there is Rotterdam. The idea is that if the weather forecast is bad, if the water tide is very high, etc., then there is a decision that this thing is going to be closed. Okay? They, at those days, 1996, 1997, decided that these decisions to close these kind of things should be software controlled. Whether this is a good decision or not, let's not debate this here. This was the decision that was taken. And the idea was in particular to also use model checking techniques. So SPIN, the model checker by Holtzman, was used here partially, not for the complete code, but for the, let's say, the critical parts of the software. To give you some impression, if you push the button, then it takes 5 hours to close those arms. So it's not something which is very similar, it's very simple. And one such arm is as big as the Eiffel Tower. So you have some idea about the size of these things, right? So, and then there is of course an economic effect. The harbor is unreachable if this thing is closed. So actually nowadays it's headline news in the Netherlands if these things are going to be closed. Typically it's once per year, because that means that for a certain period the harbor is not reachable. That means economic loss, and that's a severe loss. So here is a picture of the real thing. So here you see such an arm again, and here you see one over here. And indeed, there is a paper in 1996 that called Formal Methods in Design. They used model checking to find bugs in the software. I can confess you that they found several bugs in the software. I'm not saying there are no bugs anymore. I'm only saying they found several bugs in the software by then. Good. The last example I give you, success of model checking is a big project in Microsoft. So Microsoft XP in 2003, they found out that 85% of the crashes of Windows XP was caused by bugs in actually the device drivers. Now, device drivers are typically the things that, let's say, Microsoft themselves do not develop, but they are device drivers by, for instance, HP, if you use a HP printer, or some other kind of company. Yeah? So this was a big warning, and from that point on, Microsoft decided we are going to make a big project, and a big project in terms of Microsoft means real big. So they basically, I don't know exactly the size of the team, but they hired several people, and the aim of that group was build a model checker to find these bugs, period. So what they do is they build a model checker called SLAM, and what it does, it automatically checks device drivers for properties, and their specification is, of course, Windows uses APIs, and those APIs basically specify how the device driver should react and how it should react if certain stimuli is being sent. So the specification was given by those device drivers APIs. And actually nowadays, this SLAM model checker has been made in Windows by Microsoft. It has made it to be a standard component, like you use a compiler, like you use a static analyzer in C like Clang. The people in Microsoft use SLAM as a standard verification tool for device drivers. So what they do is they take a C program as input, the C program basically the device driver. They abstract this into a Boolean program, and then they apply what they call abstraction refinement. And then actually they also support recursion. And how do they do this? Actually, they do not only do model checking based on automata, but actually they use push-down automata. You know from automata theory that they are much, much harder than finite state automata. They use symbolic model checking techniques to combat the state space explosion. They do some analysis of pointers. Can pointer X point to something else at some point? And they concentrate on safety properties. In lecture number 3, I'm going to precisely tell you what is a safety property. But think about it for the moment, it's a kind of a monitor. It's very similar to the, no, it's gone here. Similar to the monitor we had over here. And that's what they do. Here is a graphical representation. So they have a program, then they make an abstraction, they check a property on the abstraction. If the property holds, you're done. If the property does not hold, you maybe have to do some refinement. So the way to do that is they do not take the C program, but the first thing they do, they abstract and just presume or assume that everything is simply Boolean. So you don't have the information anymore that x equals 20, you only know whether x is maybe less than 20 and larger than 20. Yeah? Boolean. So you abstract from many information, and of course you may abstract too much, then you have to refine. But if you abstract enough to just check the property, you're done, and that's what they do here. So they use this for the development of Windows 7. They found 270 bugs, 270, in 140 device drivers, so 2 bugs roughly on average for every device driver. And the code that they are checking is about 30,000 lines of C code. So the code of a device driver is about that size, maximally, that can be treated by SLAM. Good. If you're interested in more information, there is a nice paper, Communications of the ACM, which is a popular, scientific popular magazine that does actually gives a report on this model checking success. A story I like a lot is the following. It's this company. The company is called Monoidics. This was developed by those 4 people. This is Peter O'Hearn, that's Dino Di Stefano, and the other 2 people I don't know. But these are professors from a university in London. And what they developed is they started their own company called Monoidics. And what they were doing is they were interested in proving properties about programs that manipulate pointers. Now, I hope that you have ever written a C program with pointers and you know how difficult it is to get all the bugs out, right? So what they try to do is, why can we not develop a checker, a model checker, that can check automatically whether you never have a dangling reference. So you never say you dereference X and X is pointing to nowhere, which gives a bug. Yeah, these kind of properties. So no pointer exceptions. Memory leaks. And they started this company. They developed software for 4 or 5 years. At some point, they launched a company in the US. And then in 2013, it was headlines in the UK because Facebook acquired the assets of this company. So nowadays, Peter O'Hearn and Dino De Stefano are heading the formal verification group in Facebook. Yeah. Now, I'm not sure whether nowadays Facebook is good to mention with all the information about. But I think it's impressive to see that those kind of companies are investing in model checking. Yeah. One of the developers, one of the people involved in this device driving, is actually nowadays at Amazon. And he told me recently they have a group of 15 people, which for Amazon is very small. But you can imagine that they have a group working on model checking and formal verification in Amazon, yeah, which I think is fascinating. Good. What are we going to do in this course? I'm going to tell you first what are models. So I'm going to explain you transition models. We're going to see how you can transform a program into a transition system. We can show you how you can go from a hardware circuit to a transition system. I'm going to explain you things like multi-threading, communication, etc. on the model level. And we have an example modeling language, which is a nano version of Promula. Then I'm going to explain you what are properties. We first are going to take, I would say, the simplistic view, everything is linear, so infinite sequences. And we're going to see that safety and liveness properties are very important. Actually, what we are going to see that every property is either a safety or a liveness property or is equivalent to the conjunction of both. And I'm going to explain you what is fairness. Then we're going to first check regular properties, regular in the sense of regular languages. So this is just to start easy with finite state automata. Then we're going to, it's a model where you accept infinite words, and I'm going to use one of these kind of models, which are called Buggy automata. Buggy automata are not regular, but they are omega regular, and I'm going to explain you what that means. And we're going to see an algorithm which is based on depth first, but it's a nested depth first. It's a depth first search, and inside the depth first there is another depth first search. Yeah, interesting, I hope. Then we're going to see how you can express properties, and there we're going to use logics. So the first, I would say, 7, 8 lectures are not with logics, but then we start introducing logics. So I'm going to introduce linear temporal logic, the logic developed by Pnueli in 1977. Syntax, semantics, what can you express in this logic, what can you not express. Then we're going to deal, and that will be the core, how to do model checking of a transition system versus LTL. I'm going to give you the connection between LTL and Buggy automata. And we're going to see that the complexity in terms of is it n squared, is it exponential in n, plus complexity in terms of is it p-space complete, is it in co-NP, etc. Then we're going to have another logic where you're going to interpret this not on sequences but on infinite trees. And I'm going to use that computation tree logic. This is the logic that Clark and Emerson in 1981 originally proposed. Syntax and semantics, what can you express? In particular, we're going to see that this logic, the expressive power is incomparable to LTL, which means certain properties you can express in CTL but not in LTL and vice versa, and they have a common fragment, and there's also something nice that you can say about this common fragment. We're going to show algorithms, complexity, fairness. Then I'm going to explain you a bit how you can make models a bit smaller. And that's based on equivalence relations, pre-order relations, bisimulation. Then if you make the model smaller, which properties are still preserved? Such that if you do the model checking on the smaller model, what conclusion can you draw about the original model? And I'm going to explain you a bit about minimization. The course material is based on this book. Good, lectures. There are 2 lectures a week, Tuesdays and Fridays, but try to regularly check the course webpage. For instance, next Tuesday, 8:30, there will be no lecture. Maybe it's good, maybe not. But and the next lecture will be next Friday. But the best way to keep track on when is the next lecture, go to the website. And the website you find here. The slides are available on that website. I now understand that this is a chicken egg problem, right? The best is to go to my website of my group, and there you can find a bullet teaching and then you see immediately the courses we teach this semester, and one of them is model checking, and there is all the information. So we don't use L2P, right? Some people ask me, why are you not using L2P? Because the drawback of L2P is it's not publicly available. Yeah? I like to make what we are doing also in teaching available to the entire world and not only to the students in Aachen. So those slides are available to everybody, and I think that's good. I will have lecture slides. I will make them available every time before the lecture, and before means before. Could be 2 minutes before, could be half a day before, but typically not a week before. The book, I already mentioned something that you didn't hear before, but you can also, if you really want the book, there are many copies in the library. So don't get me wrong, I'm not using this course to make royalties, yeah, such that I can buy a second house in Hawaii, because I'm not going to do this. Yeah? But I just only want to make this very clear. Exercises. There is an exercise class every week on Monday. We start on April 30, still some time to go. Christian Hensel and Matthias Volk are the two people that are going to assist you there. The idea is that you get weekly exercise series that are supposed to be worked on with 2 people. I'm, by the way, very happy that there are so many people in this lecture. I hope you all take this course. That means that you are supposed to work on groups of 2 students. We will make every Monday the next exercise series available via the website. And the first time we're going to do this is on April 23rd. You have to hand in your solutions a week later, before the exercise class. Okay, this is 10, 12 is also fine. The exam is on the last day of August, and then there is the next exam on the 21st of September. This is a written exam. You are eligible to participate in the exam if you have gathered at least 40% of all the exercise points. We are not going to be a police agent and going to check whether you copy your solution from your neighbor. Yeah. If we really see this regularly happen, it might be the case that at some point you will get an appointment in my office. That's okay. Or maybe it's not okay, but what I'm saying is that if you want to discuss with your other group members, please do so. Yeah? But don't make it on Sunday evening that you just copy it, because you will not pass the exam if you don't do the exercises yourself and not think about those exercises yourself. This is maybe an open door, but I would like to stress this. You get a bonus of 1 grade if you have at least 70%. Yeah? So rather than a 2.7, you can get a 2.3 for the exam if you do this. And then I think I get to almost the last slide, then I get to your question. It's about the theoretical foundations of model checking. So today I was giving you more what's the impact of model checking, why is model checking important? From next on, it's theory. Yeah? So I'm not going to explain how to use a spin model checker. I'm not going to explain how to go from industrial requirements to formal requirements. This is not part of this course. The course is really about theory, automata, language theory, regular words, final state automata, automata for infinite words. We're going to see quite a few algorithms. Depth first search I already mentioned, some other graph algorithms, algorithms to find counterexamples. We get some data structures, some about computability and complexity theory, in particular complexity theory for LTL model checking, and logics. Good. If you have taken this course, what can you do else? Well, a lot. So I sometimes give a course which is called Advanced Model Checking. Next semester I give a course on how to do model checking of systems where you have random things. So then you're not only interested in, can my system eventually reach to a deadlock, but you would like to know what is the probability that this happens. I also give a course on probabilistic programming next semester. There are various lectures by Christoph Löding. One of them is Automata on Infinite Words, which goes much more in depth on things like Büchi automata and variations of it. There is a lecture by Professor Erika Abraham about satisfiability checking. where you actually, one of the applications of satisfiability checking is to do model checking. She also extends this to hybrid systems, systems where you have discrete and continuous things. And actually in that course, she does also verification or model checking of hybrid systems. And there are various seminars in various groups. Questions? Yes?
Is it possible to work in groups more than 2 people?
Yes, it's possible to work in larger groups, but I would say up to 3. Given this number of students, I would be happy if you adhere to at least 2. Yeah. I know that sometimes people, can I also do it alone? I prefer not to do this in this course, given the number of students here. Are there any other questions? Yeah, sorry.
How do we submit exercises?
We will make a post box at my chair, and you can put your solutions in that post box. Yeah. I will check with my assistants whether they also do allow PDFs or whatever. That's also possible.
Can we maybe also hand them in just before the...
Yes, you can hand them in just before the... I made a typo, the 10 o'clock. I mean, if you hand them in before the exercise class, because the idea is that in the exercise class, we will give you the solutions to those exercises. Yeah?
We should handle one solution for the whole group?
Yes. Yeah. Yeah. Other questions? No? Thanks a lot. Hope to see you next week. Friday is the next lecture.